I'm a computational designer, which is one design expert in architecture design. So we use computer programming primarily to produce architecture design. So without like drawing and modeling 3D with mouse, we just code or use a parameter in visual language. So then today I'm gonna talk about agent-based approach in my practice. So I use agent approach in some projects and then other more conventional type of computation in other design, but I focus the first part today. But as a general introduction in computational design, in kind of larger scope in computational design, when we make code, there are three main areas to apply those methods. And then one is like kind of design engineering. So you have some design, but you need to kind of improve or solve certain engineering problem. But another is two more, the data-driven design, the imaginative design, and which is actually, I'm going to explain a little bit more in detail. And then so design engineering is like especially when I work with another architect and they have their design, but they have problem, like there's some structure issues, the cost issues, the construction issue. And in that case, some design needs to be optimized to provide better performance, or sometimes another type of process is called rationalization, which is actually make it the design efficient to construct, to produce, so to match with certain material property, or if you building with bricks, so that shape needs to be changed for the certain structural property. So that kind of process happens. And another part called data-driven design. I mean, all of the categories are something I named, but for example, when you want to design something which is providing really good solar performance, and you have idea to take environmental data, and then you conclude design from that data, but you design the process of how to read the data and how to translate that to geometry or architecture. So that's a data generate designs. And then another example is like when you have like a data circulation, or you have idea of using circulation, and you want to provide a building which is very efficient for certain circulation. In that case, you do take data and analyze and think about how to convert this data into building shape. So that's what this approach does. And then the last category is the imaginative design. This is more about the creativity. Like if designer think of Fibonacci number as a design inspiration, and if we want to use that, we need to think about how to translate or how to use in where. Do we use for structure, or do we use for like a facade design, or do we use for like a plan design or room location or layout? So, but the think how to use those mechanisms in design is kind of designer's kind of imagination. Then so, but doing that by computation. And another idea would be like when we have this robots, I mean, yeah, drone or robots, if they become a building block of a building, then what can we do? So what kind of building we can build out of robots when robots building something which is actually already happening in some area, or building become a part of column or part of wall, etc. In that case, what kind of building we can build. So, but in this case, simulating that requires kind of coding the idea into like to make shapes. So that's another type of computational design. And then but today, so all three also they have different tendency. Like engineering problem is more like a really engineering problem with mathematics, etc. But the second one more scientific, and the third one very creative and artistic. And usually architecture project is really kind of complicated, having each aspect. So it's actually not really simple to have pick one, but that's a kind of what we are doing in projects. Then today, so those approach use many different algorithms, a very conventional, simpler one, top-down one, to a bottom-up agent approach. So then they actually towards the bottom, the imaginative one can easily can take the agent-based approach. But today I show some example of each. Okay, some of them, and from my practice in the past. And then, so first, actually, I'm gonna start more in the engineering aspect. And then, so the image I'm showing right now is a project of a skyscraper in Paris. And then the architect is called Morphosis Architect. Okay, that's where I used to work. And then, so this was a project which was supposed to happen, but the Lehman shock killed the project, so it doesn't happen anymore. But actually we did a site work and then stopped. But anyway, so this is skyscraper with the same height with the Eiffel Tower, and then close to 300 meters. And then, so in this project, one engineering problem is to build a diagrid. So this is a diagonal column to support the building and the skyscraper. And actually, there's another about main the central structure, which is made out of the elevator core, but this is an external structure. But conventionally in architecture or simple architecture design process, a diagonal grid is built on surface. I mean, it's still type of grid, so you need a 2D coordinates, and in any form of 2D. So certain surface is needed virtually, and then the grid is built on that. But to match with very specific boundary condition, if we want to have the line perfectly matching with a certain cut line, that doesn't necessarily need much, and then it doesn't naturally match. So we have to do something. We cut into pieces, but we always have problem discontinuity, and so that's one problem. And then what the solution is to put all vertices as agent, and then they figure it out. So they try to manage the spacing equal, and they try to match the tangency. So okay, so there's a like a spring. Actually, so this is more like a physical simulation, but and also this is already kind of established like more than 10 years ago. So it's actually not new thing at all. But then the term for this technique is like a mesh relaxation. And then, but so this one uses tension and also special force to maintain the tangency between one another. So this is to make the line smooth and continuous, which has a certain benefit in structure performance. I mean, if it's discontinuous or there's a kink, that's as we point a little bit. But the second part of the project is that there's a rationalization aspect in this project, which is to make building efficiently and actually too cheap to build in the cost-efficient price. When we have all different slightly different size column or angle, or that has the impact in the cost. If you have like a slightly different angle, the triangle between need to fill the glass window, and that means all different shapes. So it wants to be same shape to be cost efficient. But that part is that to make that happen, this process of repeating same geometry is actually not simple problem at all. So actually, that's not complicated problem for agents to solve. It's actually something a person can pick this area to be can be same, and this can be so it's a manual problem. But what agent is doing is stitching them together. So it's regional problem. So this place look like a repeatable, this place look repeatable, but between them to maintain continuous efficient structure, the agent is always sticking together. So when I hide this color, you don't really see the end of the region. So that's what agent is working with. So that's another problem in engineering aspect. And then yet another aspect. So another part I worked on is a scheme, which is the exterior facade of skyscraper. And this is a solar shading panel made out of metal mesh. So this panel is for solar performance, solar shading. So the purpose is to cast shadow for interior. So to do that, I put agent on each panel, and they are searching the best performing angle or location, or I mean orientation. So, but in this case, agent search the solar location through ear, then find the the height or azimuth of the altitude of the sun, the highest sun through year, and then we adjust the angle or location based on that. Actually, location is fixed, and then just only the angle. So in this case, this is a little bit more. Agents don't really interact with each other, so it doesn't need to be agent based. But later we have problem of like how to clean this panel with brush, or if maintenance person comes, how can person reach the outside of panel? So there's a gap issue, etc. Then another one issue of the gap is that person need to reach the outside. Second problem is that person cannot follow. So there's a many more constraints comes later. So this agent approach can work in that kind of solver of that problem. But anyway, so the first part of solar optimization, as a result of each of them optimized for each, their own orientation. So they are optimized for different time of actually the highest sun is always the summer solstice. So in the summer solstice days, when the sun comes in front of the panel, they are adjusted for that. So that's one technique I used. Another project, the same architect, morphosis architect, and this is Emerson College, Los Angeles, which is a satellite university campus of art school. So actually, this building is a dormitory and also the classroom in the middle. And then I designed the courtyard facade for the dormitory. So this is for the kind of for privacy for students who's living in this dormitory, but also to create a really dynamic and creative atmosphere in the courtyard or public area in this satellite campus. Then, so the panel is made out of folded aluminum sheet, but the formation has a certain constraints, several constraints. And one, obviously, the panel cannot collide each other. And then second part, the density wants to be maximized like for expression purpose. And the pattern wants to be responding to the building in the middle. And then for another constraint, I want the pattern of like opening and closing have certain rhythm in every floor. So that's a corridor for students to walk around. And so I want to have like open and close and open. That's one constraint for architecture design. But another constraint is a really hard constraint for coming from regulation, which is smoky back. So each panel cannot be closed more than 50% for in case of fire. So that's a regulation. So that's another constraint to solve in the design. Just to provide a solution, I use the agent-based. Actually, this is again close to the physical simulation, the particle base, and so particle can only move around along the structure, and then they connected with the tension and spring, and then each line is converted into 18 panel types, actually 19 or something. So then pattern is actually controlled by the particle control, influenced by the force field. So I kind of adjust the force field to solve all the constraints at the same time. So that's the particle simulation as a soft solver for all the constraints. So that's how I determine the layout of the panel. So that's the result. Then you can see the like rippling looking thing, like the bridge is kind of penetrating the building, and it looks like creating the ripple. That's one of the constraints. Actually, I designed the force field to create that kind of layout without breaking other constraints. Then another type of algorithm I use is actually the swarm algorithm is a kind of traditional algorithm, and started in 80s in computer graphics field, or more for movies. But in architecture, there's a bit many architects are interested in using this logic or this aesthetics in like 2000, and there's a bit of trend there. But the question is, what can we do with it? I mean, as the aesthetics are complex and then continuous, but what do we do with it? So for example, one issue is how can we use this shape for building or physical material and structure? So once I have the attempt to attack that, so I try to build a shape in that with solution to structure. Okay, using this swarm trajectory as one of the structure. So to do that, what I did was first I start with swarm simulation. It's typical swarm rule of there's a three main rules for swarm. But there's a two more agents behind it. There's the vertical line is the trajectory, actually not just trajectory, they are moving around, which is a simulation of a tension structure. And then there's a horizontal line or the triangular thing in horizontal, that's a compression structure simulation agent. So those two structure agents is kind of pushing each other to find the optimum structure out of this trajectory. So then when it reaches the equilibrium, that is the buildable, realizable structure in real space. So that's the result. And in a sense, this is something I'm calling a self-optimization, but basically, if you don't do that, you cannot build that shape directly. It doesn't really stay in the shape. It's just gravity just push and pull and then mess up the shape. But the agents are kind of constantly changing the size, changing the spacing, changing the length of the wire. So then that can hold the shape. Then that's the result. So that's one attempt I had before. And another application of the same approach is when I design a pier. And this is just a project, so it's not realized at all. But I used swarm formation to generate suspension bridge, okay, suspension pier. So the previous installation was a kind of suspended structure. So this is suspended bridge, like a half bridge, so it's pier. But the first part was formation. The second part, so next one is the structure simulation part. So the compression agent and then tension agent. Then when they hit the equilibrium, that's the part that the structure is optimized, so that can be built in that way. Then so that was actually just a proposal for some magazines, but yeah, kind of imaginative project for London, Thames River. Then another algorithm I use is the Cellulose Algorithm. So Cellulose, actually, in the beginning, I was just impressed. Actually, I was always impressed then about how kind of cell can grow. I mean, then even science hasn't really discovered all the mechanisms yet, but some of them are discovered. But in architecture, for my investigation, just starting with simple. So just starting with it's like a base particle, but the particle can divide into two, and the particle also has a size, so they push each other. Then I developed very highly topology sensitive one, which is they always know the linkage or connection between the cells. There's another several more types of cellulose algorithm developed by other researchers or architecture designers, which doesn't really use the kind of junction or linkage as the information. But in my case, I can't always maintain the one. In this case, the condition or like a mechanism to like when to divide into two or when to grow is based on the topology. Like when topology is this condition, and then when it divides and the new child cell is located in a very specific topological condition. And then, for example, if the cells always maintain the link to left to right, and even when you make new child agent, you just insert on the line. In that case, that link never is broken, and then so as a result, it creates this kind of brown or coral looking shape. And another case of logic, when the three cells are making a triangular face, and the new child cell is inserted in the middle. In that case, it creates a little bit kind of fluffy surface geometry. And then another logic, when child cell is inserted in the middle of the triangle, and then in that case, it always creates this kind of really pointing sharp geometry. And another case, quad condition in the middle, still pointing but less sharp. because it's quad instead of triangle. And then actually here I'm trying to get a smoother geometry. So in this case, I'm more hexagonal to more polygonal shape, and then insert in the middle, it's less sharp, and then I can getting smoother. And then I noticed that when, especially when the one cell is surrounded by 6, it's kind of start creating regular or a little bit more regular geometry. And then, so in this case, it creates very specific geometry. I mean, it started from a tetrahedron, and they go into more this tubular, like a more equal type of shape. And then I insert certain randomness, like sometimes not only 6 is the condition or trigger to create a new child, but the 7 is also randomly accepted. In that case, it creates a bit irregular, but blobby, and then smooth and blobby, but slightly irregular. So by the way, so that was kind of my investigation, just to go through what kind of form I can produce. So that this is another mechanism of like each agent can divide, say, only once. So in that case, only the newest child or cell can divide, and that creates a kind of tentacle shape. And then if I allow twice randomly, so that second time always create a branch, and so it's more, more kind of branchy coral shape is created. And there are a little bit more complicated logic of combining the previous one too. Somehow it creates the branch, but as a group, or the growth always happen as a group, and the branch always created as a group of cells kind of dividing together. And it is kind of blobby, thicker branches. Then by the way, so that was a kind of a series of investigation. And then in this case, I applied another external environmental factor of like growing only to upwards. I mean, assuming some plant growth, etc. Then once I applied this for architectural design, actually more like an interior design. But in this case, what happened is I grow the shape out of initial geometry, and then grow. I control the where can grow more and where can grow less, etc., which related to some construction issues to create this lighting fixture. So for some interior design and in cafeteria, a little bit structure shape, but this is created. And also there's another process of more like a buildable shape. So that initial one is kind of buildable but unstable. So I optimize the structure in the same kind of way of the previous one, like a tension structure, compression structure. This is just some common digital fabrication technique to produce with CNC machine efficiently. But anyway, then so that's created as a lighting diffuser / sculpture / certain kind of lighting installation. So that's what I applied where I applied the agent approach. And then so this one approach is the ideation part. I start with the idea of what happens if I grow shape with those algorithms, and then later combined with other engineering issues, to fabrication issues, to cost issue, and kind of going back and forth and as parameter. So those are practice. And then from here, actually, a little bit more in research aspect, but in architecture discourse, there's a certain discourse of like, I mean, agent-based system for sure tends to generate more organic and nature-inspired shape, and the biomimicry design is one huge area in this architecture design and other area of design. But following nature is a bit actually the very traditional thing in architecture. But also organic architecture is very active in contemporary architecture since 90s, or more free shape and continuous shape. There's a certain discourse that we in architects, and we tried this many years, several decades. And but should we also think about the world of artifacts? We also have the heritage of like the construction, thousands of years of development, how to construct things, how to make things. And those are, some people think that those are forgotten in a way, in the design research. So some people start seeing the other way, not nature way. And then in this way, so in this case, they claim like the issue of modularity, like a module and the different parts, articulation, that's not really happening in nature. And then that, but for us to build something that's actually important. So to make a buildable things, that's they claim that's important. And then partially it's kind of true that, especially like in my like 10 years or projects of like a swarm approach, and they are continuous and smooth, but for building that's quite problematic. And you don't see like a module anywhere. And then that's so that criticism is quite valid. And then certain the diversity is there, but still like there's also singularity there. Even in this simulation of like branching of more organic thing, you kind of see the different size of cells across area, but when you think of modularity and how to build things in parts, there's nothing we can do, kind of. So they claim we should look into. So there's a new trend of looking into this thing among computational designer and architecture designer. However, my counter criticism is that nature actually does that. They have very distinct parts, and their articulation really highly done. Not because my the simple design, swarm design I produce as well as kind of singular and continuous, but that they don't have like a difference of body to the actually I don't know how to call this part, like a side arm part or back part. That's very different thing. Nature actually creates this out of one mechanism or DNA, but my agent system doesn't do that. Even in like the leaves of plants, that's kind of module already. So they do this. Simply our agent system is not that advanced enough to achieve that yet. So that's actually my kind of point of stance to that problem. And then what I'm trying to do recently is so it's actually issue of like a bottom up, top down in a way. When we do the bottom up, we kind of lose control. And then so if we want to, for example, if we want to achieve the distinction of the body parts to the side parts, maybe we have two agents, but that's top down. You have just set up two different things, or environment, you can set up the environment to do control that. But I don't want to, so top down, bottom up combination have always trade off, you sacrifice some parts. But I kind of want to stay fully in bottom up in agent, and then but still want to think about the module and then this articulation, like the layer of leaves already, or like a different body part, etc. How can we achieve that out of one agent? So that's my interest. And I came up with the idea of stacking body clock, which is, so instead of agent building module and then using that, why don't we use agent who can build the module, but also can build a next level module. So it's a hierarchical module, but by having hierarchical behavior. So what I mean is that, for example, if an agent has 3 different body clock, in a way like every second agent does one thing, every minute every agent does another thing, and then every hour agent does yet another thing. So in this case, 3 levels of behavior you can design. So for example, so in this case, a 2-level agent, like if the bottom level is just going straight and the counting, and then every 4th count, it click the higher body clock and it turn 90 degrees. Great. But if you have like a third logic of in the third clock is ticked, it branches to specific direction, in this case straight. But in the 4th clock, it turns 90 degrees again. So in this case, creates square of square. And the 5th body clock, and it creates another branching. So it has 2 different levels of branching, small square branching and big square branching. And then you can also have another, so 6 levels, 7th level. So it's a kind of infinite level of stack. So that's my idea. So create to solve the issue of modularity and hierarchy in agent. Then once you do that, basically now you have one agent to design, but you have layer of behavior to define. So in this case, the top layer is having like not 90 degree, but like 180 degree turn. And in this case, level 1, like a bottom clock is having slight bend, but all other agent is trying to make a regular grid. But the bottom level is kind of messing up, so it doesn't really create a regular grid. And then this is just a more extreme angle. And then you can also control the randomness of like in different levels. So this is the highest level randomness. So each level module, bottom module is very regular, but branching in a very different moment. But in this one, like a second or third level is randomized. So as a global scale, it's creating regular grid, but the square, like a middle square is all different size. In this case, the bottom level timing is all random, so it's all off. Like a small cells are created, but as a whole, it's a bigger one. And then this one is like combining like a random angle with the random timing in the middle level. And then so this one is like all of them, like bottom level randomized, higher level randomized, and the angle is randomized. But you start to see the organic quality, like original, like a more nature aspect as well. So I'm trying to have like both of them, the artifact world to nature world, to be integrated together. So this kind of resembles like an ancient like buildings. But anyway, so those are just like example came out of this algorithm, and then let me skip through that. It's where that time is up. So, but anyway, if you are interested, this video is on YouTube, so you can check. Then just additional topic of like, actually this is just showing another example. So I could rebuild the like a conventional geometry out of the logic of these agents, like a hierarchical agent. But if I go back and then adjust each level of behavior, then yeah, I can reproduce something else, but still having the same hierarchy. Then the slightly different algorithm from that, or actually in architecture or in engineering, there is an issue of like a swarm robotics or reconfigure modular robots to construct something. So in architecture, we start building like 3D printing building, a robot fabricated building. That's already happening right now. But the next thing or in the future is like these robots becoming building. So not robot building using some other material, but the robot is material of building. So in that case, of course, yeah, those need to be controlled in agent logic. So there's many different ways to do, and then this is just a very static logic. But another example would be like this one is using the Cellulose Algorithm. So they try to insert the new robot is inserting itself in existing robots to grow as a dome. So that's another. But again, the clock stack building, clock stack algorithm is using in this case of assuming there's in the future in the issue of like a space architecture, like similar to the International Space Station, like, but in this case more massive scale. In that case, how they can deliver the building block by itself, and what will be what kind of the shape will be the idea for the extra. So that kind of investigation going on as well as a kind of ongoing future work. That's it. Thank you very much.